Hello again. So in category theory in particular, perhaps, it's very tempting to turn our tools onto themselves, which is what we're going to do today. We're going to see if there is a category of categories. And strictly speaking, there isn't because of size reasons, but we are happily going to ignore that and turn on type in type like we normally do when we do category theory, so that we don't have to worry about such bureaucratic issues. So let's see. So we want to define a category of categories. So what I mean by this is that I want my objects in this category to be categories themselves. And then, of course, I need a natural notion of morphism between categories. But this is what we saw last time, right? This is exactly what a functor is. So we see that we might have some hope to make a category where the objects are categories and the morphisms are functors, because we said these are the structure preserving maps between categories. Okay, so in order to finish this, we need to show that there is an identity functor, and we need to show that we can compose functors, right? So let's start with the identity functor. So this is supposed to be something which, given a category C, gives me back a functor from C to C. So let's see if we can define this. Okay, so a functor has an action on objects. So here, given an x, which is an object in C, we have to give back an object in C. Well, we can just give back the same x. Right. And given a function f, or rather a morphism f in C from A to B, we have to give back the same thing. So we do give back the same thing. And then we have to see that this preserves identities, but that's obvious. And we have to see that this preserves composition, but that's equally obvious, right? So it's not that hard to make an identity functor. It's just the identity on both components. Okay, and then here we also need to be able to compose functors. If I have a functor from A to B and a functor from B to C, then I should make a functor from A to C. Right, so just copy that. Functor, so that I have A, B, C, and they are categories. Then I can compose them like this. Okay. Let's see. So I need an underlying action, which should be a function from objects in A to objects in C. Well, I can just, so this is just a function between sets now, right? Because this is a set and this is a set. So if I compose these in the, as functions in set, I can take the action of f and the action of g, and that does the right thing. Right. Okay, and here I also need to act on an f. So here, let's see if we can read this. So we need a morphism in C between g of f of A and g of f of B, right? And we have a morphism in A between A and B. So if I use the f map part of f and apply that to f, then that gives me a morphism in B between the action f of A and f of B. So if I now also do f map of g of that, capital G, then that really does the right thing. Right. Okay, but let's check that it preserves identities. So this is what we need to prove, but I know that f preserves identities, so this should be an identity in B, and then G will preserve that in turn. Right. So if I do identity of f, con of f map G of that, that's the good first step. So I can use transitivity of that in the second step, and the second step is just identity G. Okay, and similarly here, preserving composition, so f will preserve this composition, and then G will preserve the resulting composition. So I think it's the same as this, but instead of identities, it's homomorphism proofs. Yeah. Okay, so that can be my composition. Right. Okay, but now we have to show that these things are associative, and if you're not careful, then this is a mess, right? So actually prepare the piece of kit that we need. It's going to look rather horrible how you prove it, and even the statement is a bit interesting. So this, I claim, is how you prove that two functors are equal, f and g. So first you need to prove that they are equal on objects, and then you need to use that proof to fix up the types with the subst, so that you can say that the action on maps of f equals the action on maps on g. So you would like to say they're equal on objects and they are equal on fmap, but fmap, the type of fmap itself, is actually mentioning the action on objects, right? So you need to fix up the type of this with the previous one. So let's not worry about how you prove this, and let's see how you use it instead, because it looks scarier than it is, I think. So here we have to show this, and we are claiming that we can do this with our piece of kit. So we're trying to show that two functors are equal, right? This composite versus this composite. So we have to give a proof that they are equal on objects and a proof that they are equal on morphisms. And on objects, we see that we are lucky. This is exactly REFL. And that means that in this scary type up here, we are substituting by REFL, which means that the substitution is going to go away, and this is just going to reduce to fmap of f, which is going to what's going to happen a lot in practice. It means that it's not so scary to use, and then we see here again that this is just REFL. Right? And it's going to be a very similar story here, where we are lucky. This is literally the same thing, up to an eta contraction at least. So REFL works, and then here this is the same thing again. And identity right is going to be the same story. Okay, so we have successfully constructed a category of categories. It means that the concept is useful enough to describe itself, which is reassuring, I suppose.